Right, today we are going over chapter 18. This chapter is titled Aromatic Substitution Reactions. So since we've already seen how aromatic pi bonds are less reactive, we saw that in the previous chapter, chapter 17. Let me get my pen out. Where this reaction is not reactive unless we put in some type of reaction conditions. And the reaction conditions that we introduced, we added iron here. So it says, however, when iron is introduced, a substitution reaction does occur, and 75%. The observed reaction is electrophilic aromatic substitution. And this chapter really is going to talk about, electron withdrawing groups, electron donating groups. If you put a group here, or if it's like this, what's going to happen with the reaction? That's kind of what we're going to talk about today. So it says electrophilic aromatic substitution. An aromatic proton is replaced by electrophile. The ring acts as a nucleophile. The aromaticity of the ring is preserved. So you can see that we are preserving the aromaticity. We still have those three bonds right there, even though we added a substituent. So it says in bromination of an alkene, a bromine functions as an electrophile. That means it's going to accept the electrons. So a Lewis acid catalyst is needed to make bromine electrophilic enough to be attacked by the more stable p electrons of an aromatic ring. So this is our Lewis acid catalyst. And they show you the mechanism on the next slide, but I want to give you a moment to take some notes. All right, so the mechanism is this right here. So FBr3 activates the bromine, making it even more electron poor. You can really see in this case, yeah, it's it's supposed to be 7 minus 6. That's how you get the +1 on the formal charge here. So it's electron poor. So then it's going to really want to be that electrophile. Now, if it's just a bromine plus, you can really see, this wouldn't even be here. It'd just be a +1. It's really going to want to accept the electron. So we have the bromination of the benzene mechanism. Now that we have our catalyst, in the first step, the aromatic ring functions as a nucleophile, forming an intermediate sigma complex. Notice how we're moving the positive charge right here. It can be moved around. But note on this one, it never comes right here. We're not putting the positive charge right here. You can either put it here, here, or here. It does become a big deal where that positive charge ends up. Later on in the chapter, you'll see that. And then we can have a proton transfer. So we generate HBr here. So aromatic ring attacks the electrophile. A sigma complex intermediate is formed. And step 2 is the deprotonation of the sigma complex. And you can see that right here. Here's the deprotonation. So that means we're going to make it aromatic again. So re-aromatization. We can see right here. So addition reaction to an aromatic ring would be endergonic, which is why substitution is observed instead. Endergonic means higher in energy from where we started off at. You can see that. Exergonic, this is exergonic. We're going down in energy. So that's why we're seeing the substitution product. So aluminum tribromide could also be used as a Lewis acid, a catalyst for the bromination of benzene. The mechanism for the bromination would be the exact same. So here we have the addition, or the substitution, of the bromine. Here we have the substitution of the chlorine. So benzene can also undergo chlorination, but it doesn't work well for fluorine or iodine. That's because chlorination is too violent to be practical. It's too reactive. Iodination is generally slow with low yields, and that's probably due to iodine is a pretty big, it's larger compared to chlorine or bromine. So we're really going to only see this with chlorine or bromine. So you have the chlorination or the bromination. So note the EAS mechanism for chlorination is analogous to the bromination, and I show that to you right here. If you want to, you can find these in your book on page 792 and 793. So please note that EAS stands for electrophilic aromatic substitution. And it says, in fact, all electrophilic aromatic substitution reactions discussed in this chapter follow the same two-step mechanism. So, they're all analogous with each other. So we have a nucleophilic attack followed by the sigma complex, and you can see the sigma complex right here. All we're doing is moving the charge around the ring, and then we have a proton transfer. So then they go on to this concept in 18.3, which is on page 795, called sulfonation. It occurs by using SO3 as the electrophile. So when they're doing this, in the book, it says they're using fuming sulfuric acid. Fuming, and they say it right here, which fuming contains H2SO4 and SO3 gas. So that's what this contains. So when we do this, we're going to put this SO3H group right here. So we're going to sulfonate our compound. And again, this works the same way. You're going to have a nucleophilic attack. You're going to have a nucleophilic attack right here, followed by your sigma complex. Remember, your sigma complex is just the ring, and you're just moving around that charge. And then followed by a proton transfer. So just like we saw on the last slide right here, it's the same exact steps that are happening. You have a nucleophilic attack, followed by your sigma complex, and you have a proton transfer. So it says SO3 is a potent electrophile. The sulfur atom has a significant partial positive charge due to inefficient pi overlap with the oxygen atoms. It says, as a result, the SO bond has a significant single bond character. So that means, we're not really overlapping the best right here. Now, if this would be, another atom that it could overlap and we'd have a better overlap here. But you can see that we're not going to really have this overlap that we want. We're missing this portion right here. So the sulfonation, so we have the nucleophilic attack. So in the first step, the aromatic ring functions as a nucleophile, forming an intermediate sigma complex, and here's your sigma complex. That positive charge here, it can be stabilized by resonance. So in the second step, the sigma complex is deprotonated, restoring aromaticity. So we're going to restore our aromaticity here. And we do get a proton transfer right here. That's how we get our SO3H product. And they give some examples in the book where, sulfonation is used. You can use it for food coloring. You have red 40, and then you have yellow 6, and orange 1. And they said a good example of this is when people are eating their Fruity Pebbles, that they're using these dyes to color the Fruity Pebbles. So sulfonation is sensitive to reagent concentration. It's a reversible process. So the next one is sorry about that. Next concept is nitration, and this occurs by using HNO3, which is strong acid, as a source of electrophile, and H2SO4 is the acid catalyst. So it says it is believed a nitronium ion is the active electrophile. So what do we mean by nitronium ion? They give you, that's why you have to use sulfuric acid as a acid catalyst. Here we have a proton transfer right here. This right here is a good leaving group. It's just water. So they'll take off, and then you have the nitronium ion, which is an active electrophile. I mean, look at this charge right here. We have a positive formal charge, 5 minus 4 equals +1. All right, so once we have our nitronium ion, so we're going to have the nitration of the benzene. So we have our nucleophilic attack, right? Once we have a nucleophilic attack, we'll form the formal charge. We can move that formal charge due to resonance. That's our sigma complex. Then we have our proton transfer, so we can, reestablish aromaticity. So a nitro group can be reduced to form an amine. So once you have this nitro group right here, if you react with these conditions, you can form an amine. And why might you want to put an amine on there? You might need it for drug synthesis. And they talk about that on page 799. It says the discovery of prodrugs. Or they have to put an amine group on there instead of the nitro group. So that's a good reason to know how to do this reaction. So we talked about bromination, we've talked about chlorination, we talked about, sulfonation, we talked about, putting a NO2 group on there, and then we can switch it to an amino group, NH2. Now we're going to talk about an alkylation. So an alkylation occurs by using an alkyl halide as so what do we mean by alkylation? We're going to add some type of alkyl group, right? So the catalyst functions as expected. So here, you know, we're having this chlorine being transferred to the aluminum, and we form this carbocation here. So this would be a good, again, this would be a good area for a nucleophilic attack. Let me show that right here. So then we alkylated our benzene group, right? We added this group to it. All right, so once we do that, so simple primary halides can be used effectively. So we can add that ethyl group on there. So since primary carbocations cannot form, the electrophile is presumed to be a complex. So we have this complex then. And this complex can be attacked by an aromatic ring, much like we saw during the chlorination mechanism. And we can also get a mixture of products with this, because think about this. We could have a hydride shift. Well, not on this one, but on a propyl group right here, they're showing this right here. I guess it's a butyl group. So we can have this 1,2 hydride shift. If we do that, we can form a secondary carbocation. And we've learned from previously from organic 1, a secondary carbocation is more stable than a primary one. So we can have, different products. And we see that this one's formed 65% of the time. And that's because we have that rearrangement. If we have a positive charge here, where is the attack going to occur? It's going to go like that, right? So we'll have, and 65% of the time where the secondary carbocation is formed, we'll get that product. The other 35% would be where the primary carbocation forms. All right. So there are 3 other limitations to Friedel-Crafts alkylation. The halide leaving group must be attached to an sp3 hybridized carbon. So what kind of hybridized carbon is this? This is an sp2. Again, this is an sp2. And if you had this, let's just say this is an sp, there's going to be no reaction. So it has to be, an sp3 hybridized carbon. You only know that from experimentally doing this too. So if you don't experimentally prove it, then you can't, say it's, whether it happens or not. All right. So it says polyalkylation often occurs. So that means we're alkylating on both sides, we're not just alkylating on one side. So, we're alkylating on both sides in this case. And it says some substitute aromatic rings. And the reason why this is not going to occur Remember, oxygen, this is going to be electron withdrawing. So they're going to be electron withdrawing groups. Remember, you can have electron donating groups, but in this case, electron withdrawing, and we're not going to get a reaction here. So acylation and alkylation both form a new carbon-carbon bond. It says acylation reactions are also catalyzed by aluminum trichloride as the Lewis acid. They go on and show you how to do that on this slide right here. The active electrophile is an acyl ion. We have that positive charge right here. So we can get a nucleophilic attack followed by our sigma complex. But it's always the same thing. Once we have this right here, we have our nucleophilic attack. Then we're going to follow this by our sigma complex. And then followed by a proton transfer. So it's kind of a three-step process. So the active electrophile is an acylium ion. Sorry about that. So we see this right here in this mechanism. So acylium ions are resonance stabilized and not subject to rearrangement. So we have resonance stabilization. Once we get past that, so then we see our acylation mechanism. We have our nucleophilic attack followed by the sigma complex and then the proton transfer. Same steps that we've seen for all the rest of the mechanisms in this chapter. And that's and this group right here is your acyl group, right? So we formed our acyl group. And then there's an important reaction. It's called the Friedel-Crafts acylation. So it says some alkyl groups cannot be attached to a ring by Friedel-Crafts alkylation because of rearrangements. So an acylation followed by a Clemmensen reduction is a good alternative. So here's your Clemmensen reduction right here. So let's see, Clemmensen reduction right here. And you see what we do? We get rid of this, don't we? So this is gone. So the product right here, you know, this is called an aryl ketone. And we reduce that with this zinc, mercury, HCl, and heat. And you have to, and if you did this in a lab, you'd have to be careful about using this. Number one, you're using HCl. This is no joke to work with. And then you're using zinc, mercury, which if you've read about mercury, mercury poisoning is real. So if you ever do this in a lab, a Clemmensen reduction, please be very careful and do this in a fume hood. You would not want to be breathing in mercury vapor or HCl vapor either. I've worked a lot with mercury in the past, and whenever I was working with mercury, I was very, very careful on how I was working with it. So polyacylation is generally not observed, which is the problem with alkylation. So that means we're not gonna add on another group like this, is what they're saying. That, you know, we're not gonna get another reaction. And the only way to know this, again, you'd have to experimentally do this. You can't just like look at this. Otherwise, you could just keep on drawing more stuff and then start, you know, acylating the other spots, but you'd have to experimentally determine this, and then you'd run your NMR experiments or your mass spec or your FTIR to determine this. So two issues arise when adding a group to a ring which already possess one or more substituents. So in this case right here, remember we were doing this before we had nothing on here, right? Now we're adding this methyl group on here. So, you know, what's going to go on with this? So just consider the nitration of toluene. So what is the effect of the methyl group? Remember I talked about, so this is going to be electron donating. So we can call this this is an electron donating group. It says toluene reacts much faster than benzene. The methyl group is electron donating, so they put that there for you, making the ring a better nucleophile. So then it talks about the regioselectivity, you know, and there is some regioselectivity. What do we mean by that? Where are we going to add this NO2 group? Are we going to put it here? Are we going to put it here? Are we going to put it here? You got your ortho, meta, and para position. It's like, okay, where are we going to put it at? Well, it's going to preferentially prefer the ortho position. And that's due to the stability of the sigma complex. Remember the sigma complex? We're going to be moving around. Oh, I shouldn't have dropped. We're going to be moving around that that positive charge, aren't we? You know, we're moving it around. I just want to see, and they show it. Okay, so they so you know, regional selectivity, we're going to put it preferentially in the ortho position, right? And I'm going to show you on the next slide why that is. You know, at 63% of the time, it's going to go in the ortho position. Look at this. In the meta position, it's only 3% of the time. Well, that has to do with the sigma complex. So, you know, this effect is from the sigma complex. So we're going to look at the sigma complex on the next slide. So we're going to compare the relative stability of the sigma complex intermediate. So we have this addition, and then look where the positive charge goes in this sigma complex, right here. You know, the positive charge, if we're going to take this right here, the positive charge would be right here, right? We can move that positive charge here. We can also move it here. And remember, this is electron donating group, right? So because of that, you know, because the ortho and the para attack has a positive charge, delocalized adjacent to the, so it's adjacent, you know, this is adjacent right here. Adjacent to the electron donating methyl group, this gives a more stable sigma complex intermediates because they're donating electrons, so it's going to be more stable. And here, this positive charge never comes here, does it? It does not come here. We're not seeing it right there. I should put an X through there, but then you might get confused with the positive, and let's just erase that. But we're not seeing that charge ever coming adjacent to that. Look how far away we are. We're this far away, or we're this far away, or we're this far away. You know, we're never adjacent, are we? Here in the para attack, we are adjacent. So that's why, even though, you know, in the meta position, we're closer than the para, it even prefers the para position because we can put that charge adjacent to that methyl group where we have this donating going on. So I thought this was a really interesting slide, in all honesty, when I was looking over this. And they show us the reaction stabilities with the potential energy versus the reaction coordinate. And the one position that is the least favored is this one. So we'll call this the least. And this is the most favored at the ortho position. The sigma complex from the ortho and para attack has a positive charge delocalized adjacent to the electron donating methyl group, given a more stable sigma complex intermediate. So they show it the charge adjacent. We can never get adjacent with the metal group, so it's going to take a lot more energy for that reaction to go through. And it says the ortho and the para products predominate, very little meta product is formed. So more ortho is formed because there are 2 ortho positions and only 1 para position. So that kind of makes sense, right? If you have an ortho position here, I should just call it O. You have one right here. Okay, we have a greater likelihood because there's just a greater possibility because there's 2 positions versus just 1 para position, right? So you have 2 versus 2 ortho versus 1 para. It's just due to probability at this point in time, you know. So we have more positions in the ortho position. That's why we see it's almost a 2-to-1 ratio, right? If we'd multiply 34 times 2, we get 68. So it's almost 2-to-1. So I think this is a good time to take a break right here. So we're going to go ahead and take our break, and we'll come back. Let me see what time it is. We'll come back at 11 o'clock. Welcome back, everyone. We're going to continue on. Let's see, we'll go to screen 2. We just talked about this. This is where we left off at. We saw that the ortho position was much more highly desired than all the other positions. So the methoxy group in anisole activates the ring 400 times more than benzene. So the methoxy group donates electron density via resonance. You can see how it can donate electron density via resonance because due to the lone pair of electrons on the oxygen. So the methoxy group activates the ring so strongly that a Lewis acid catalyst isn't necessary, and the polysubstitution is difficult to avoid. So we're going to get polysubstitution, no matter what. We're going to get it in the ortho and the para position. These activators are generally ortho-para directors. Then you can almost imagine why we're not going to get much of anything in the meta position. Well, that's because if you draw this out, you're going to see that the positive charge is never going to be right here for the meta position. We're not going to have this. So that's why we're not seeing the bromination on the meta position. We get a little bit of it. I shouldn't say we're not going to get hardly any, because you can see right here we got 2%, but that's very little compared to the ortho and para position. So like the methyl group, the methoxy group is activated in an ortho para director. And they show you the resonance stabilization of the sigma complex. So here we're seeing the sigma complex right here. And here we can see in the para position, it's more stable. So we're forming more of this because it takes less energy right here. And you can see it takes a lot less energy than the ortho position. So we're directing it more towards the para position, even though we have twice as many positions. It's just for this case, it's going to go in the para position. It says the nitro group is an example of a deactivating group. It is both inductively electron withdrawing and withdraws electron density from the ring via resonance. And you can also think about steric hindrance right here too, maybe while we're directing it. And the well, no, this is a nitro group. Sorry about that. So the nitro group is a deactivating group, so it's going to be electron withdrawing. That's because we have this positive formal charge here, so it's going to want this electrons from the aromatic benzene group. So it's going to want these electrons to satisfy itself. It says nitrobenzene undergoes nitration 100,000 times slower than benzene. So, not a lot going on. In this case, the meta product is the major product. So in all the other cases, we're seeing the ortho and the para, but in this case, we're seeing the meta. Now this is electron withdrawing. It's taking away the electrons. And that's because if we put a positive charge here, how would that donate? It's not going to help contribute to the electron withdrawing effects. Here, in the meta position, we don't see that formal charge adjacent to the NO2 group. So if the positive charge is right here, this is going to contribute to instability. It's going to make it unstable, and so we're going to see the same effects with the para position. And they show us an energy diagram here. So the nitro group is a meta director. So all electron donating groups are ortho-para directors. Electron donating groups, what did we see? Remember toluene? This was electron donating, and they are ortho-para directors. All electron withdrawing groups, we just had an example of electron withdrawing group, didn't we? With an NO2 group, that'd be they're meta directors, except the halogens. Halogens withdraw electrons by induction, deactivating. So halogens donate electrons through resonance, ortho-para directing. And I talk about halogens on the next slide. So halogens withdraw electrons by induction. Halogens also donate electrons through resonance, ortho-para directing. So you can see an example of that right there. Halogens donate through resonance. We can see that right there. See, in the ortho-para position, we can stabilize that that formal charge through resonance with the halogen. We're not seeing that in the meta position, though, are we? This is the two I want you to look at right here. So that's why it's going to prefer the ortho, and that's why it's called an ortho-para director then. So here's some strong activators, ortho-para directing, moderate activators. So, you don't have to memorize this. This is all here for you. So strong activators are characterized by the presence of a lone pair immediately adjacent to the aromatic ring. So what do we see here? These lone pairs of electrons, don't we? So a moderate activator exhibits a lone pair that is already delocalized outside the ring. And there's another one, alkyl groups are weak activators because they donate electron density by the relatively weak effect of hyperconjugation, and that was described in chapter 6. And these are weak activators. There's no electron pairs for them to donate, so they're not going to be as strong as are the other groups that we just talked about. So strong deactivators, they're meta-directing. And that's due to the resonance and induction. And they talk about moderate deactivators are groups that exhibit a pi bond to an electronegative atom, where the pi bond is conjugated with the aromatic ring, and we can see some examples of that. All right. Then we have our weak deactivators right here. And we've already talked about the electronic effects of halogens. So remember that halides are the only deactivating groups that are ortho-para directors. So they're deactivating, but they're ortho-para directors. And they have a really good summary in table 18.1. So now they're talking about multiple substituents. So the directing effects of all substituents attached to a ring must be considered. In these reactions. So the directing groups of the methyl and the NO2 group direct the bromine to the same carbon. One product is obtained. You can see, okay, this is an ortho-para director, right? We talked about this being a meta-director. Oh, sorry about that. This is ortho-meta-para. I should put this in 2 different colors, and then let me change the color real quick. And then for the nitrogen group, I'm going to go with blue. So this would be ortho-meta. So you can see now that they're both at the ortho-meta position relative to what it was, whether it was the methyl group or the nitro group. So we're going to preferentially put it right here. So if the groups direct to different carbons, the stronger group will dominate the effects. Then we have to see if it's a strong director or weak director. So, let's see what we have going on here. Take my pen. So this is a ortho meta para. Let's change the color. Red. I wouldn't be putting it here anyway. So we know that the that CH would be a ortho, but since this OH is a better director, the NO2 group is ortho to the stronger OH group. So steric hindrance must be considered when more than one product is possible using these guidelines. For a monosubstituted ring, the para product typically dominates due to sterics. Then we're talking about ortho meta para. It says the para product typically dominates due to sterics. Remember, this is an ortho para director, right? But this is going to occur at the para position. In this case, there's some sterics going on here. So this is going to be our major product. And that's due to steric hindrance raises the energy of the activation energy. So, if we're just considering, I'm just doing this on the fly. We're doing this, and we both start at the same position. That means, this one, so this activation energy right here is smaller, isn't it? So it's going to want to go here then because we have a smaller activation energy. The steric hindrance must be considered when more than one product is possible. So they give us another one. So for the 1,4 disubstitute aromatic ring, no, this is our 1,4 disubstitute aromatic ring. The regiochemical outcome of this reaction is controlled by steric effects. So the nitration is most likely to occur at the site that is less sterically hindered. So of the sites that we have to pick from, we can only pick from 2 sites here, right? We have 2 sites to pick from. And where is the less sterically hindered site? Well, it has to be at site number 2 right here. I'm putting this at site 2. I mean, if we're to look at this, this would be 1, 2, 3, 4. So this would be either at the 2 or the 3 position. And we're going to go pick the 3 position right here. And that's going to be our major product. Now let's just say that we move this up right here. And that's what we're going to do on the next slide. So for the 1,3 substituted rings, substitution typically does not occur between the existing substituents. So we're not going to see this right here. This is not even going to be observed. We're going to put it on the side that has the least sterics. We're going to put it right here. Remember, an alkyl group is a, if we were just looking at this right over here, this would be an ortho meta para director. And let's change our colors. This is an ortho meta para director. So we basically have two sites that we can put. We're going to see some of the meta, but not a whole lot. Remember that? We're definitely not going to put it here, and we're going to see a small amount. It's probably really not negligible, but this is the site we're going to see because, we have the least amount of sterics. So least amount of sterics. It says, consider how one might force a substituent to add ortho instead of para in the presence of an ortho para director. So a blocking group could be used to prevent substitution at the para position. So remember, these are ortho para directors, right? But what if we put a methyl group right here and we block it right there? If it's blocked right there, how is the bromine going to add right there if there's already a group right there? So the bromination is going to preferentially occur at the ortho position. And that's because we have a blocking group, and they spell that out for us. And then we can get rid of the blocking group, and then we have our bromine in the ortho position. And there's other blocking groups too. It says sulfonation, since its reversal is commonly used as a blocking group. Remember how easy it was to reverse the sulfonation group? We just used dilute sulfuric acid, and we can reverse it the other direction. So the synthesis can be accomplished as follows. So we have this group right here. We have a tert-butyl group. We add our fumine H2S2O4. Remember, this is going to be an ortho para director, so we're going to be putting it right here in the para position. And it's really not going to occur in the ortho position because, this is a big tert-butyl group right here. So then our bromination is going to, we're going to want to selectively put, there's only really one spot to put the bromine group, and that's in the ortho position, isn't it? And then if we reverse the reaction right here, we're going to get rid of this SO3H group, or sulfur trioxide group. So we're going to get rid of that, which is dilute H2SO4 going in the reverse direction. So this is really interesting, concepts going on now. So 10 different groups can be installed on a benzene ring using the reactions covered so far. There's your 10 different groups. And then they go on to say, okay, so synthesis of a disubstitute benzene ring requires careful analysis of the directing groups. So which one are you going to put on first, the bromine or the NO2 group? And since the NO2 group, the nitro group is a meta director, we're probably going to put the nitro group on first, then followed by the bromine group. If we put the bromine group on first, then the nitro group is going to go on either ortho or para, and that's not where we want to have the nitro group. And remember, why will we do this? Because some drugs will want to be an NH2 group, so we could replace that with an NH2 group with the reaction we talked about earlier. Pull that reaction out real quick. To get this to an NH2 group, all you do is add iron or zinc HCl plus NaOH. We convert that to NH2, and that could be more useful, for drugs. So functional group conversions that change the directing effects. And they talked about this on the next slide, didn't they? Exactly what I was thinking about. Converting the NO2, the nitro group, to an amino group. Also, you can change the directors. This is a meta director. This is an ortho para director. So, here we have this CH3 toluene. We can convert that to a meta director by adding, we can oxidize it, KMNO4, H2O, and some heat and an acid. We talked about the Clemmensen reduction, didn't we? Using this, we're going to get rid of that ketone, and we have an alkyl group now. And here we use excess NBS to convert this to CBr3, which now would be a meta director. Say additional consideration is necessary when one of the groups require more than one step to install. Groups need to be meta, but both constituents are ortho-para directors. So in this case, we have both ortho-para directors. So it says we need to take advantage of the meta directing ability of the NO2 group before reducing it to the NH2 group. Okay, so that's a smart idea. So in most cases, changing the order of the reactions will change the substitution pattern on the ring. So first we're going to add the nitro group, right? We're going to add that nitro group first. And that's going to be a meta director. So we're going to add the chlorine. Once we have the chlorine there, then we're going to add this right here and convert that into our amino group. I guess it'd be these two. We do this, get here. So other limitations that must be considered when planning a synthesis: nitration cannot be done on a ring that already contains an amino group. Okay. It says the region, and it gives an explanation in the book. It says the reagents for nitration, which are a mixture of NH3, NO3, and H2SO4, can oxidize the amino group, often leading to a mixture of undesirable products. It says attempts to perform this reaction often produce a Terry substance. And a Terry substance is a dark, oily, viscous material. It's just not gonna work for what they want it to be done with. It may have some usefulness on other applications, but generally not for what they were using it for. But another person's junk might be another person's treasure, so you never know. There's other limitations that must be considered when planning a synthesis. Friedel-Crafts reactions do not work on a ring that is moderately or strongly deactivated. So here we have moderate and a strong deactivator, and we're not going to get our Friedel-Crafts reactions to go through. So when we come to 18.13, it says a nucleophilic aromatic substitution is a reaction where the benzene is attacked by a nucleophile. Okay. So here the OH is a nucleophile and the bromine acts as a leaving group. So in order for a reaction like this to occur, there has to be 3 criteria. One, and they talk about it here, but one, the ring must contain a powerful electron withdrawing group. And where's our powerful electron withdrawing group? It's probably good to stay here. It's right here, right? The ring must also attain a good leaving group. Well, okay, I should be working on the other side. Here's a good leaving group. I'll call it LG. And the leaving group must be either ortho or para to the electron withdrawing group. If the leaving group is meta to the nitro group, the reaction is not observed. So if we put our bromine here, we're not going to see this reaction go through. This would not happen if it were in the meta group. But that's not the case. If we're in the ortho-para position, we can go ahead and do this. So and they call this complex, so we have a nucleophilic attack. And the nucleophilic attack will be by the OH group. And then instead of a sigma complex, this is going to be called a Mesenheimer complex. And we talked about the 3 criteria here. So let's go on. We talked about the no reaction here. But with the electron withdrawing group in the meta position, it is unstable to stabilize the Mesenheimer complex. And the Mesenheimer complex is kind of like our sigma complex. Here we see the Mesenheimer complex right here. So we have our nucleophilic attack, followed by our resonance stabilization. And they call this the Mesenheimer complex. And that's probably due to the person being the person's last name being Mesenheimer discovering this complex. It says, note for the Mesenheimer complex, this intermediate exhibits a negative charge, right? Remember, before we had a positive charge for the sigma complex. This is a positive charge, wasn't it? But here we're having a negative charge that is resonance stabilized throughout the ring. So we're stabilizing this negative charge through resonance stabilization throughout the ring. So in the second step, a leaving group is expelled to restore aromaticity. And you can see finally, we are getting rid of that right here. If we come down here, come right here, let's put here, we'll put our here, and this will be a good leaving group. It says the substituted phenol product is deprotonated under the basic hydroxide conditions, so acidic workup is necessary to attain the neutral organic product. So if we have this, if we use, let me see, what did they use right here? And that's why you have this acid right here. Otherwise, how are we going to protonate the final product right here? Oh, sorry about that. We went too quick. And what do they mean by that? That means if this is just basic, you can deprotonate that, right? Well, how are we going to protonate that again? Well, we have to use an H3O+. So acidic workup is necessary to attain the neutral organic product. So that's how we get our neutral organic product right here. And I think that's a good spot to end off at. I mean, we've gone through a lot today. I hope you enjoyed this lecture. I thought it was really insightful. Leave your comments to see, if you have any questions, let me know. You're free to go, and I'll see everyone on Tuesday.